The discovery hypothesis, time, isolation, and the measure of discovery. Introduction, models and rhythms. Your heart does not look like the jagged line on an ECG. Yet that line is a crucial model we use to measure and describe its rhythms. The peaks and valleys are not the heart itself, but they reveal something essential about how it beats. Physics works in much the same way. Einstein's equations, quantum probabilities, and the curves we draw on graphs are not the universe itself. They are models, indispensable ones, that let us measure, predict, and describe. They give us access to rhythms of motion and time that we could never see directly. What follows is what I call the discovery hypothesis. It is not a new physical theory, but a way of thinking. That time, as we experience it, is inseparable from discovery, and that relativity's time dilation can be understood as isolation reducing the rate of discovery. This perspective does not undo relativity, it reframes it. The universe does not need to conform to the shape of the lines we draw upon it. My aim is simply to explore how discovery and isolation shape our sense of time, and to invite reflection on what our models reveal and what they cannot. Superposition as epistemic ambiguity. We must distinguish our use of the term superposition. In physics, superposition describes the linear combination of quantum states. Here, I use it in a different, epistemic sense, as a description of our knowledge before discovery. Until a signal reaches sensors and collapses alternatives into record, multiple possibilities remain live. This is not many realities at once, but the persistence of unresolved descriptions. Discovery as collapse. Collapse is the arrival of epistemic data, the moment when ambiguity becomes record. Isolation's role. The greater the isolation, the longer superposed descriptions persist. A particle behind a barrier. A ship whose signals have not yet arrived. A star beyond our reach. Or remain suspended in epistemic ambiguity. Humility. Probability is a map of expectation, not the territory of reality. It charts what we might discover, not what is. Thus, superposition here is not an ontological claim about reality, but a dramatization of the gap between being and knowing. 2 times, ontological and epistemic. Ontological time, the actual unfolding of real events along world lines, independent of whether they are ever discovered. Epistemic time, the sequence of discoveries. Ticks as received, signals as recorded, the heartbeat of knowing. Relativity compares proper times across frames, but observers access those comparisons only through delayed or redshifted signals. Time dilation appears not as slowed being, but as slowed discovery. Ontological time never stops. Epistemic time can. And epistemic time is fragile. Records can be forgotten, erased, corrupted, or misinterpreted. A signal may arrive but fail to be archived. A discovery may be made but later lost to memory or decay. Ontological events remain in the past regardless, but epistemic time depends on the persistence of data. This distinction is the foundation. Without it, we confuse the rhythm of the universe with the rhythm of our records. Arrows of time. Time does not have a single arrow, it has at least 2. The ontological arrow, the arrow of reality, marking the actual unfolding of real events. The epistemic arrow, the arrow of record, marking the sequence of discoveries as signals arrive and are archived. Both arrows point into the past, but in different ways. Ontological past, the totality of real events that have already unfolded, whether or not anyone has observed them. Epistemic past, the archive of discoveries, the subset of events for which signals have crossed into record. At the present moment, when now equals 0, the two arrows intersect. Ontological events are still unfolding, and epistemic records are still being added, but they do not always align. Example, a supernova explodes in a distant galaxy. Ontologically, it belongs to the past the moment it occurs. Epistemically, it belongs to our future until its light reaches us. Example, two ships travel side by side at near light speed. Ontologically, they remain abreast. Epistemically, each sees the other trailing, because the signals they receive come from when the other ship was behind its current position. This is where superposition enters. Superposition is the persistence of epistemic ambiguity between the ontological past and the epistemic past. And yet, we do not only look backward, we use the epistemic past to reach forward into the ontological future. Every time we catch a ball, we enact this principle. The light reaching our eyes shows the ball where it was, not where it is. Our brain projects forward, predicting where the ball will be in ontological time, and moves the hand to meet it. The present is the hinge between record and reality, between what has been discovered and what is yet to unfold. Thus, the arrows of time can be summarized. Ontological arrow, reality, events unfold irreversibly into the ontological past. Epistemic arrow, record, discoveries accumulate irreversibly into the epistemic past. Superposition, the interval between the two arrows, where events are real but not yet recorded. Prediction, the act of using epistemic past to anticipate ontological future. The future, then, is not only what has not yet happened, but also what has happened without yet being discovered. Concurrency and immutability. If the arrows of time describe how reality and record diverge, concurrency describes how records are brought into alignment. In relativity, simultaneity is frame-dependent. What counts as at the same time depends on the observer's motion. In epistemic terms, concurrency is the coordination of discoveries across observers, the weaving together of separate archives into a shared chronology. Ontological concurrency, events unfold in the actual fabric of reality, whether or not they are ever compared. Epistemic concurrency, observers exchange signals and synchronize records, agreeing on an ordering of events within a chosen frame. This coordination is never perfect. Signals are delayed, redshifted, or lost. Two observers may disagree about whether events were simultaneous, yet still converge on a consistent record once enough signals cross. Concurrency is therefore not absolute but negotiated, a consensus built from partial discoveries. Immutability is the counterweight to this relativity. A discovery, once recorded, does not unhappen. The archive may be reinterpreted, but the entry itself remains. Example, astronomers once recorded canals on Mars. Later data reinterpreted them as illusions, but the fact of the original discovery, the records of what was seen, remains immutable in the archive. Example, two ships exchanging signals at relativistic speed may later reconcile their records, but each signal received is fixed in its own log. The discovery cannot be erased, only recontextualized. And yet, immutability has limits. Epistemic time depends on the persistence of records, and records themselves are fragile. They can be forgotten, corrupted, erased, or left to decay. Concurrency can only weave together what survives. The ontological past remains intact, but the epistemic past is always vulnerable to loss. Thus, concurrency and immutability work together. Concurrency ensures that isolated records can be synchronized into a shared chronology, while immutability ensures that once discovery occurs, it cannot be undone. But the fragility of epistemic time reminds us that even the archive of discovery is not eternal. It must be preserved, or it will vanish. Space as a rotational hierarchy. Consider a glass resting on a table. To the observer in the room, the glass appears perfectly still. Yet from orbit, the same glass is spinning with the Earth. From the Sun, it is racing around a star. From the galaxy, it is swept along in a spiral arm. What seems motionless in one frame is restless in another. Thus, space is not emptiness, but a hierarchy of rotations. Inward, toward atoms and electrons, outward, toward planets, stars, and galaxies. Each frame defines its own conditions of rest, but each is nested within a larger turning. Discovery is the act of shifting frames, realizing that stillness is provisional, and that every frame belongs to a hierarchy of motion. And this is where curvature enters. The curvature does not live in the universe as a physical bend in some invisible fabric. It describes our motion through this hierarchy of rotations. The Earth turns, the Sun orbits, the galaxy spins. And when we project those rotations into equations, the lines curve. The curve is in the map, not in the territory. All matter is on many curved trajectories within many frames of reference. Every particle, planet, and galaxy is inscribed in countless arcs at once, each curve belonging to a frame, each frame provisional. Relativity formalizes this truth, that motion and curvature are inseparable, and that what we call rest is always relative to a chosen frame. When models say time stops, some models of physics suggest that time itself can stop, but what they really describe is not the end of time, but the breakdown of connection, the point at which discovery can no longer cross a boundary. At the speed of light, an object receding at light speed becomes unreachable. Its signals never arrive. Ontological time continues, but epistemic time, the record of discovery, ends. For the photon, if the two ships were traveling at the speed of light, they would not see each other, or anything at all. A photon carries data forward, but never accumulates its own record. Without epistemic data, time does not exist for it. At the event horizon, to an outside observer, an infalling object seems to freeze. But this is only because the signals we receive come from when the object was behind its current position. Inside, proper time continues. At the singularity, even internal communication fails and the observer becomes isolated from itself. We can measure what falls into a black hole. We can measure what escapes. Radiation, jets, faint whispers of Hawking's prediction. But what happens in the interim is not measurable. This is not because nothing happens, but because discovery cannot cross the boundary. The shared lesson: ontological time never halts, but epistemic time can be cut off. When models say time stops, they are really describing the isolation of systems beyond the reach of discovery. Isolation and discovery in relativity. Isolation is not confined to photons or horizons. It can occur even in ordinary motion. Imagine two ships racing side by side at half the speed of light. Ontologically, in their shared frame, they remain perfectly parallel. Yet what each crew sees is different. Looking across, each ship appears slightly trailing because the signals they receive come from when the other ship was behind its current position. The lesson is stark. Proximity is not enough. Two ships can share the same journey, yet remain cut off from one another's discoveries unless their signals are carefully aligned with the geometry of motion. Even in shared motion, discovery lags behind reality. This is precisely what relativity describes when it speaks of time dilation. In special relativity, a moving clock appears to run slow because its signals, its ticks, take longer to reach another observer's senses. Discovery is stretched. In general relativity, a clock deeper in a gravitational well appears to run slow because its signals are delayed and redshifted as they climb out. Again, discovery is stretched. Thus, we can restate the principle. Time dilation in relativity equals isolation, reducing the rate of discovery. Mathematical interlude. Discovery and isolation. Discovery over isolation equals K. Discovery equals signals received, the record of events, epistemic time. Isolation equals barriers to signals, the degree of separation in space-time. K equals a constant, reminding us that discovery and isolation are always bound together. This is not a physical law, but a philosophical invariant. Relativity shows that signals take longer to reach senses when motion or gravity increases isolation. What we call time dilation is simply discovery slowed by isolation. And this ratio matters because it reframes time itself. It tells us that every clock is not just a mechanism of gears or atoms, but a balance between connection and separation. It tells us that the heartbeat of discovery is always shadowed by the drag of isolation. And it tells us that the measure of time is not only what we record, but what we fail to reach. Conclusion: models, maps, and the measure of discovery. What I have offered here is not a rival to Einstein's vision, but a reframing. His equations remain among humanity's greatest intellectual achievements, and they will continue to guide us to the stars. The discovery hypothesis doesn't undo those models. It asks us to see them differently. The curve is in the lines of the graph, not in the universe itself. As Alfred Korzybski reminded us, the map is not the territory. If there is ever to be a true theory of discovery, it will be for physicists to create. My aim has been only to sketch a hypothesis, to invite reflection on how discovery and isolation shape our sense of time. As Einstein himself said, the important thing is not to stop questioning. Curiosity has its own reason for existing. And so I leave the last word not to equations, but to curiosity itself. If time is the measure of discovery, then isolation is its shadow. And every clock, every signal, every heartbeat is a record of how far curiosity can reach. Thanks for watching the Discovery Hypothesis. If you would like to see more of my work, please subscribe to my channel, like my video, and share it on social media.